I'm Maurizio Rossi from the University of Trento in Italy, and what I'm going to talk today is our proposed strategy to assess the air quality in indoor environment. In particular, we want to monitor the natural gas presence in indoor environment with an ultra-low power technique targeted to embedded wireless networks, embedded systems, basically, because those can be in the future smart home and can provide many important information to assess the air quality and so the health of the inhabitants, basically. So first of all, we choose the more suitable kind of sensing technology to embed into wireless nodes, and we go through chemoresistive MOX devices because they exhibit a very long lifetime, they are sensitive, and they are cheap with respect to other sensing technology available on the market. Okay, because we want to use devices already available on the market in order to shorten the development and deployment. So the main limitation of chemoresistive devices is the power consumption, of course, and especially in wireless sensor network application, we have to carefully take into consideration this issue, considering that in comparison with the other peripherals found in wireless sensor, gas sensors exhibit the highest power consumption with respect to even radio transceivers that are usually the most power hungry devices. In this table, we reported a comparison of widely adopted sensors, MOX sensors, compared to radio transceivers. This one, the first one, is the one we used, and this is a well-known sensor. And we can see that power consumption, the current consumption, is even higher. So the power issue is our goal, our topic, yeah. And in order to reduce the current drained by the sensor to perform a measurement, we propose to shorten the time the sensor is switched on and to analyze the outcome, which is as usual resistance signal, through a frequency-based analysis. And our goal is achieved by reducing by almost 1 order of magnitude the energy drained by the sensing element, and we at the same time achieve an immediate discrimination between clean air and hazardous situations. This means that we don't get a quantitative measurement of the air quality, of the natural gas present in air, but we can assess if the environment is safe or not, which is most important in our target. It's our main target, since if we can see that there is an hazardous situation, we can switch on the sensor and perform a quantitative measurement in order to assess quantitatively, precisely, the gas concentration in the environment. In this field, other interesting solutions have been proposed, mainly in outdoor environments. And in this research, they used electrochemical devices and energy harvesting technique to increase the lifetime of the wireless sensor network. Other solutions introduce an adaptive duty cycles, and even new gas sensors have been proposed, MOX sensors have been proposed, but still the power problem remains, especially in indoor environments where harvesting is difficult when you have to deal with such kind of power consumption. So our setup, we use this commercial device target to natural gas. As I said, this is the characteristic curve provided by the manufacturer, valid for this environmental condition. And we use this device with this electronic board, which is a state-of-the-art wireless sensor node, based on a very powerful microcontroller, a 32-bit architecture with integrated RF module and antenna. And deep sleep consumption is only 8 microampere. The board itself embeds other sensors, light, temperature, humidity, and an accelerometer, and also an SD card holder to collect data locally. So, considering our goal, we started analyzing the standard response of MOX sensor used in a duty cycle fashion. So, when you want to use the MOX sensor, when you want to power on the sensor only once in a while, you get this particular response. This is the resistance of the output of the sensor with respect to time. And as you can see, we reported the output value for air, 0.1% natural gas, and 0.3% natural gas. As you can see, after a few seconds, you get a steady state, almost steady state response, and this way you are at this time you are able to quantitatively assess the gas concentration. We instead focus, for our purpose, to the transient response, meaning we switched on the sensor device for only half a second and extract the feature of this transient response by means of this equation, a normalized DCT function, and we focus only on on one component, around 20 Hz. We perform a set of measurements, and these are our results for two different kind of environmental monitoring situation. With a medium duty cycle, meaning the sensor is switched on every 2 minutes, and with a very low duty cycle, with the sensor switched on every 15 minutes. A measurement taken every 15 minutes, which is enough in our case, because if we want to monitor an indoor environment like this, we don't have to collect real-time data, since the gas takes time also to propagate and saturate the environment. Particularly for natural gas, since you have to reach a very high concentration in order to be explosive, basically. Our result shown that it's possible to discriminate the air quality inside the environment with this technique, with this low power technique. But the interesting feature is that if we consider our normalized feature with respect to the gas concentration, we can see that with medium duty cycle, the absolute value increases. With the absolute value of the feature increases with the gas concentration. For different environmental conditions, this behavior remains the same. With very low duty cycles, instead, we can see that there is an inverse relation between the feature and the gas concentration. But still, this characteristics is constant, changing the environmental condition inside the environment. So, in order to point out our result, our ultra low power feature, the ultra low power feature of our technique, we reported the current drained by the all embedded sensor during a measurement scenario. First of all, we collect the battery level, temperature and humidity on the environment, then we sample the gas, we process this data and save locally, and then we send to the coordinator. In particular, this graph, this current has been collected using 1 ohm shunt resistor, and the whole picture represents 5 seconds, which is the time normally one should switch on the MOX sensor in order to get a reliable response. In this case, as you can see, we have only 1/10 of the time the sensor switched on. In particular, this is the time, and this is the average current during the whole measurement phase. Another thing that one should see is that the radio protocol needs a lot of power, and this is one of our future goals, to reduce the power consumption due to the network communication. So, in order to summarize, we estimate the lifetime of our wireless sensor network in 3 different cases. First of all, in for real-time monitoring, where we compare the sensor always switched on with respect to one measurement taken every 5 seconds, and we get an 87% energy saving. Then we move to the duty cycle monitoring, which is more interesting for us. We can see that without network communication, without a network, we can achieve up to 75 weeks of autonomy of our sensor, but with the network enabled, with the protocol we are currently using, we can achieve up to 37 weeks, which is more than 7 months. So, this concludes my presentation. I presented you this ultra-low power technique to use MOX gas sensor to assess the air quality in indoor environments using commercial devices. And with this technique, we get an immediate discrimination, qualitative discrimination of the air quality, and we can achieve up to 75 weeks of autonomy with our monitoring network. For the future, we are deploying a wireless sensor network in our department, and we want to collect real data to assess the time drift, the actual current consumption, and also we want to test this technique to more devices in order to get a full monitoring of all the chemical substances that can be present, that can be harmful for human beings in indoor environments. So that's it. Thank you all.